You ever think about physics? It's this huge, sprawling thing. You've got black holes over here, tiny quarks over there. How does it all, connect? It can seem totally chaotic. But what if we had a map? Well, that's what we're going to do. We're going to try and chart the entire landscape of physics together.
I mean, the scale of it all is just mind-boggling, right? On one end of the spectrum, you've got cosmology. We're talking galaxies, the edge of the universe itself. And on the complete opposite end, you have particle physics, stuff so unbelievably tiny it basically breaks all the rules of our normal world. It's an absolutely massive territory to cover.
So, that's the big question, isn't it? How does it all fit together? How are these things related? Because, let's be honest, if you're not deep into physics, it can just look like a messy pile of random, disconnected ideas. But I promise you, there is a logic to it. There's a thread that connects everything.
And that's exactly what we're going to do. We are going to build a map of physics. Think of it like a guide that'll show us where we've been, where we are right now, and, maybe most excitingly, all the blank spots on the map that are still left to explore. And our journey begins in a time when everything seemed to make perfect sense.
Okay, so let's step back in time. Welcome to the world of classical physics. We're talking about the time before 1900, when physicists were feeling pretty good about themselves. They really thought they had almost everything figured out. In their eyes, the universe was this beautiful, elegant machine, like a giant clock, and it was all governed by just a handful of perfect, predictable laws. And the main person to thank for this tidy picture of the universe? Isaac Newton. I mean, the guy was a giant. His laws of motion, they literally described how everything moves. And his law of universal gravitation, this was just genius. It connected the dots between the planet soaring through the heavens and an apple falling from a tree right here on Earth. Same force. And maybe most importantly, he gave us calculus. That's the mathematical language that physics still speaks to this very day. So, let's put this on our map. Newton lays this incredible foundation way back in 1687. And after that, other physicists just kept filling in the details. The 1800s were huge for thermodynamics, the science of energy. And then, in 1865, this guy James Clerk Maxwell comes along and does something absolutely incredible. He manages to unite two forces that everyone thought were totally separate. Now, a really big part of this classical world was optics, the physics of light. People have been fascinated by light for centuries, right? It explained all sorts of cool stuff, like how a prism splits light into a rainbow, and how telescopes could use lenses to open up our view of the heavens. That's basically how astrophysics was born. And as you'll see, figuring out the true nature of light turned out to be, well, pretty darn important. And studying light revealed this really deep connection to another big idea, the theory of waves. You know, think about ripples in a pond. Light is kind of like that. It's energy that's traveling through a disturbance. But here's the crazy part. Unlike sound waves, which need air, or water waves, which need water, light doesn't need anything to travel through. It can zip right through the total vacuum of empty space.
So yeah, the classical world was getting pretty comprehensive. You had Maxwell, who did that amazing unification of electricity and magnetism into one thing, electromagnetism. And get this, he proved that light itself is an electromagnetic wave. Mind-blowing. Then you had other fields like fluid mechanics, which is all about how liquids and gases flow, and thermodynamics, which gave us this super important concept called entropy. You can think of it as a measure of disorder. It's basically the reason your room gets messy and never cleans itself up.
So, the big picture here, the main takeaway, was this idea of a clockwork universe. The thinking was, if you could just know the exact position and momentum of every single particle in the universe, you could, in theory, predict the entire future perfectly. Everything was determined. It was a beautiful, neat, tidy picture of reality. But a few tiny cracks were starting to appear in that perfect machine.
So we're at the turn of the 20th century, and physicists are feeling pretty confident. But there were these little nagging problems, a few experimental results that just wouldn't cooperate. There's this tiny, weird wobble in Mercury's orbit, some strange behavior when you looked closely at electrons and light, things that just didn't fit the clockwork model. And by poking and prodding at these seemingly small problems, physicists were about to unravel everything.
This didn't just add a new country to the map, it completely shattered the old one. And in its place, two totally new, revolutionary domains appeared. On one side, you have Albert Einstein's Relativity, which is the rulebook for the universe on the grandest scales. You know, planets, stars, entire galaxies. And on the other side, you have quantum physics, the completely bizarre but wonderful set of rules that governs the universe down at the tiniest subatomic scales.
Okay,
Let's zoom in on Einstein's territory for a second. First, his theory of special relativity. It's built on this one wild idea. The speed of light is the ultimate cosmic speed limit. Nothing can go faster. And that one simple rule leads to some crazy consequences. Like, the faster you go, the slower time ticks for you. And it gives us the most famous equation in history, E=mc², showing that matter and energy are two sides of the same coin. But he didn't stop there. With general relativity, he completely rewrote our understanding of gravity. It's not some mysterious force pulling things together. Nope. It's the actual fabric of space and time, spacetime, getting bent and warped by heavy objects.
So while Einstein is looking way out at the stars, a whole other group of physicists is looking way in, into the heart of the atom. And what they found there was just weirder than anyone could have possibly imagined. You can see how our idea of the atom changed. At first, we thought it was just a tiny solid ball. Then we imagined it like a mini solar system, with electrons orbiting a nucleus. Then it got stranger. Electrons weren't orbiting, they were jumping between specific energy levels. And today, the modern view is that an electron isn't even a thing in one place. It's more like a blurry, wave-like cloud of pure probability.
And you might be thinking, okay, that's weird, but what's the point? Well, don't mistake all this weirdness for being impractical. Our understanding of this quantum world is literally the foundation of almost all modern technology. Nuclear fission, which gives us power, that's quantum. Lasers, quantum. The computer or the phone that you are using to watch this right now. It only works because we understand quantum mechanics. All right, so we've mapped out the classical world, that old clockwork universe. And we've added the two huge modern revolutions, relativity and quantum physics. But now we've reached the edge of the known map. And this is where things get really interesting. This is the land of the biggest mysteries, the place where we know for a fact our understanding is totally incomplete. And right in the middle of this new territory is what you might call the giant chasm of ignorance. It's the biggest problem in all of physics. See, we have this amazing theory for big stuff, general relativity, and we have an amazing theory for small stuff, quantum physics. They both work perfectly in their own domains. But, and this is a huge but, they absolutely refuse to work together. If you try to use them to describe something that's both super heavy and super small, like the center of a black hole, the math just completely breaks. It gives you nonsense answers. This is, without a doubt, the single biggest challenge for physicists today.
So naturally, the holy grail of physics is to bridge that chasm. The goal is to find a single theory of quantum gravity, you might have heard it called the theory of everything, a single set of rules that describes the entire universe, big and small. There are a few big ideas out there. A couple of leading candidates you might have heard of are string theory and loop quantum gravity. But so far, none of them have been proven. It's still a wide-open race.
But if you think that's the only mystery, well, hold on to your hat, because there's an even bigger and maybe more humbling one. You see, after all that incredible work, all those centuries of discovery, all those brilliant theories, it turns out that everything we've talked about so far, every star, every planet, every atom, all of it only makes up about 5% of the universe. Just 5%. The other 95% is composed of stuff we call dark matter and dark energy. And the honest truth, we have almost no idea what they are. And these enormous gaps on our map, these huge mysteries, they push us beyond just the science. They force us to ask much, much bigger questions. And that brings us to one last layer we need to add to our map, one that sort of floats above everything else: philosophy. Because behind every discovery, behind every equation, there's always a person asking not just how, but the big one, why?
I mean, these are the questions that drive physicists to the edge of that map in the first place. Questions like, what is the fundamental nature of reality? What is all this stuff, really? When you get right down to it, what are we actually made of?
And then there's an even bigger one. How come the universe even exists at all? Why is there something here instead of just nothing? I know, it's a question that sounds almost spiritual, but it's a very real and profound motivator for scientists trying to understand the Big Bang and the very origins of everything. And finally, maybe the ultimate question of them all: why is physics the way it is? Could the laws of the universe have been different? Or is there some deep, fundamental reason that they had to be exactly this way for the universe to exist? It's a question that leaves us standing right at the frontier of knowledge, just staring out into the great unknown. And that, right there, is the map of physics.